So we have 40,000 particles, let's say. 40,000. How many particles are moving at 200 speed? 38 particles. You see? Don't worry about the stuff below the negative. That's not in our bound. So we can just kind of go like this and focus on this portion. You see that? That's a Maxwell Boltzmann distribution right there, guys. You're seeing it firsthand. Beautiful.
Okay. So what was the original question?
Okay, now we can say, what's the speed that maximizes? Okay, so how many particles? In other words, it maximizes the y here. If I go here, 78. I think that looks like the maximum. 78.6469. 696. Okay, I think that's the maximum. 697. So just based on that, based graphically, the mode, the velocity mode, what we call the velocity that maximizes the number of particles, is what? 422.087. Right? 422.087. Right? Now let's use the equation to find out the velocity of the mode, and let's see if they are the same. In other words, I'm kind of trying to go backwards. I'm saying if this equation is true, maybe that's why the Desmos couldn't even integrate it, right, earlier. Remember we tried to integrate this, it said taking too long. Yeah. There you go. That also answers that question. Okay, so now what's the formula? Go to files. The velocity of the mode is called VP, V probable, square root of 2c. And what's c? Square root of RT over m. Okay, so according to that equation, what's the V probable? Or sometimes it's called most probable. What is it? Square root of 2c, and then c is equal to what? Square root of RT over m. Where is my paper? You see that? Square root of 2c, and then square root of 2c is square root of RT over m. So what is that equal to? Square root of 2 RT over m. 2, what's R? 8.314. T is 300 Kelvin over the molar mass. So if I apply this equation, it should give me graphically the same thing that this gave me. The velocity probable is 422. 2 times 8.314 times 300 divided by 0.028. Hold on, square root. Square root. Aha. Do you see that? So in other words, just simply graphing that function that we have, right? The v squared, all that, finding the value that maximizes it, it gives you that velocity, 422. Now, what's the next equation? V average. Okay. Square root of 8 pi times c, right? And now what would we have to do that? we would put c as square root of RT over m. So then we would do what? See, square root of 8 over pi, square root of c, and then square root of 8 RT over pi m. So if I put that in, what is it going to give me? Now, for a Gaussian, for a normal distribution, Gaussian normal distribution, this would equal that, right? But it ends up that for a Maxwell distribution, this is slightly larger than that. So you're going to get here 8 times 8.314 times 300 Kelvin divided by 0.028 divided by pi, the square root, 476.3 meters per second. So that means, this is kind of weird. That means graphically, you got 78 particles. If you have 40,000 total particles in that container, you had 78 particles that are moving at the mode speed, right? At the most probable speed. But the average velocity is somewhere here. What is it? 476? 476. This is the average velocity right here. I wish I could freeze that. So that would be the average velocity, and then that would be the V most probable. So why is average velocity slightly shifted to the right? Whereas in the Gaussian, they were equal. Well, one way to say it is maybe because for the Gaussian I think I'm getting tired now. For the Boltzmann distribution, this side of the graph is wider. You see, it goes out to infinity. So maybe you could say, oh, that kind of pushes everything to the right. Do you see? It's not symmetric. It kind of pushes it 476 like this. That's the average value. So how would we calculate mathematically the average value? How did I do it for the Gaussian? Let's see, what did I do for the Gaussian? Oh, remember for the Gaussian, I did this to find the average. I did x, y of x over 40. And then the average ended up to be the exact same as the mode. So for my case, what would I integrate? X times my function over 40,000, you see? So I would have to integrate, let's go to my function now. Let's copy this. Now that I have it correct, I think the integral should work. 0.028, close one more parentheses. Yeah. So 4 pi times n times 0.028 over 2 pi. This is the molar mass, gas constant, the temperature, 1.5 times what? Times x cubed. Why am I doing x cubed? Because remember, to find the average, you do the velocity times the number of particles that are going at that velocity, right? So which is, since there's already an x squared, you multiply that by x times e to the power negative 0.028 x squared divided by, e to the power negative 0.028 times x squared over, what is it? Over 2, 8.314, 300. Over 2 times 8.314 times 300. Is that right? 0.028. Yeah, I think that should work. 4 pi n 0.028 over 2 pi 8.314, 300, 1.4 x cubed e to the minus 0.028 times x squared over 2 r t dx. And then the limits of integral, we should be able to integrate to infinity now. Let's see. Okay, good luck to us here. Okay, once I get the answer, what am I trying to prove? Oh, I'm trying to prove what the average velocity is using the definition of average velocity versus the formula, right? So I'm doing the integral of the number of particles going at velocity times x, which is the velocity, right? From 0 to infinity. Notice this time it did give us an answer. 1.09. So I'm doing integral from 0 to infinity of all of that, x cubed e to the minus x squared. Okay, what did it give me? 1.905578 times 10 to the 7th. Now, what should I divide that by? The number of particles, right? 40,000. So what's going to happen? Well, let's hope for the good news here. Where's my? Okay, so here comes the moment of truth. I'll take this one. 1.905578 times 10 to the power 7 divided by 40,000. Yes, 476.3. That is the average velocity. You see how it shifted to the right from the so this is the mean velocity, also known as average velocity. It's larger than the mode. So in other words, even though most number of particles are going at 422, but on the average, molecules are moving at 476. But physically, which one is temperature connected to? Is it connected to this or this? Is temperature connected more to probable velocity or to mean velocity?
Probably mean.
It would make sense to say it's more relies on the mean, because you could say on average molecules are traveling at 476. It doesn't really matter that the most number of particles are traveling at 422. But on what matters is more on overall average, right?
Yeah, just
but
like
it ends up that even this doesn't have meaning. It's actually the root mean square velocity that matters. Okay, and what's the equation for the root mean square velocity? Go to the formula sheet. It's square root of 3 times c, which we saw earlier when we derived the PV is 2/3 n times kinetic energy, right? Remember we saw 3 pop up there. So in other words, we're seeing this 3 pop up from a couple places. One from our whole derivation at the beginning of class, and then we saw 3 pop up. But now we're seeing it from a statistical point of view that this has more meaning, right?
So it's not from the degrees of freedom?
Well, it's two ways to interpret it. It is from the degrees of freedom, yeah.
Okay.
Yeah. There's 2 ways. So now, if we calculate that, we get what? Square root of 3 times c, square root of 3 times square root of RT over m. So what is that going to be here? Let's see. So
once again, the mode was the velocity at which most of the particles are traveling, and then
the highest number of particles are traveling at that single velocity. Yeah.
At that single velocity, or is it the
at that velocity? Yeah.
Yeah, the most particles are traveling at that velocity.
Yes.
And the mean is the
mean is the overall average. In other words, it's you're taking how many particles are traveling at every velocity, and you're averaging it out for all the particles.
Okay.
It's like you're saying there's 40 particles traveling at 30 meters per second. There's 40.6 particles traveling at 35 meters per second. And then you just keep adding, which is like doing an integral, you know?
Okay, yeah.
Yeah.
So, because I'm comparing it, I'm like thinking about like in the periodic table when you get the molar mass, right? The isotopes, and you add them all up, and the abundance level.
Yeah.
Which gives you the okay.
Yeah. Except the only difference here is that it's a continuous numbers. There's particles traveling at 20. There's particles traveling at 20.001. There's 20.0002. You know, so that's why it's an integral.
Yeah. Okay.
Yeah, it's not discrete numbers.
Definitely. And then for the root mean square, that one.
Okay, now I'm going to show you how we're going to do that.
Okay.
Yeah. So we're basically almost near the end, but yeah, it is kind of dragging out. 3 times 8.314 times 300 over 0.028. Okay, so now 3 times 8.314 times 300 divided by 0.028, and then square root of that. Okay, so now V root mean square is 516.95 meters per second. So that's even faster than the V mean, right? So graphically, it would be somewhere here. 516, you see here? So the V root mean square is this one, 516. See, only 71 particles are traveling at the V root mean square, whereas the V average was what, 476? There is 76 particles traveling at V average. And then at V most probable is 78 particles traveling, you see? So the V root mean square is more here, okay? Now, how do we physically calculate the root mean square? What we do is we find the average of the squares of the velocities, and then we square root them. So in other words, here's what you're doing. You're saying there are particles traveling at 20 meters per second. There's another one traveling at 20.001. There's another one traveling at 21 point something, so on, so on. So now let me square all those velocities, right? Then multiply how many particles are traveling at those square of those velocities, right? Add them up, divided by the number of particles, then square root them.
It reminds me of when we do like standard deviation and stuff like that, right?
Yeah, it does resemble that. In other words, the reason why you're doing that is because the kinetic energy of each individual particle depends not on its velocity, but its velocity squared. So since the energy of the particles is more important to you, you want to know the energy of each particle, average out all the energies, then square root them to find the meaningful velocity. You see? So you're saying, I don't care how fast the particles are moving. I care what their kinetic energy is. So let me find the kinetic energy of each particle. What's their average kinetic energy, right?
Yeah. Oh, so then that's why it's 1/2 mv squared. So that's where the okay.
Yeah. So now here you go to the integral table, and you're gonna integrate x to the 4th. You see, not x cubed. Why? You see why it's x to the 4th?
Because the original function had a
the original distribution already had an x squared because it was
Gaussian or
no, not a Gaussian. Gaussian is the other one. It was a Boltzmann distribution, right?
Yeah.
So now you're doing times an x squared. Okay, so now you're gonna do an x to the 4th. That's why it's good to have the integral here, and now you just change it to x to the 4th. Then go. Oh, it's much bigger, right? Then divide this by 40,000, then square root that. You see? That should give us the root mean square velocity. Okay, so let's go, let's write that down. 1.069 times 10 to the 10th. Okay. So now 1.069 times 10 to the, let me write down more sig figs. 1.0692139 times 10 to the power 10. Okay, so now divide that by 40,000 and square root that. Ha! There you go. 516, 517. Yep. That's the root mean square velocity. Man, that's beautiful. So when you're really getting it, it's like, oh, just things are just placed. And then now you can kind of see why this is the more meaningful velocity, because this really represents the velocity that determines the average kinetic energy of the particles.
Yeah.
See? In other words, it's the velocity that tells you at what kinetic energy, on average, each particle is moving at.
Mm-hmm.
Right? So again, it's shifted a little bit more to the right, like that.
Then that goes back to our whole temperature and how we're not just looking at it at the macroscopic, but the
yeah. But the interesting thing is, this is the genius of Boltzmann. How did Boltzmann come up with a distribution, right? A distribution function just based on the statistical mechanics,
Hmm.
which when normalized, it gave you the same root mean square function that we got by not even considering any of this, by just simply doing the derivation based on degrees of freedom. That's the real wow of this whole lecture, right?
Yeah.
How does this function, which represents a statistical representation of molecular speeds, how does this give you the same root mean square with the 3 in there? You see, that's why the guy should have gotten a Nobel Prize for that.
Wow.
Yeah, that's the real wow. In other words, to describe the 3, not simply because of degrees of freedom, by simply just, okay, this function normalized the way that it behaves, when you find the square of the average of the squares and then you square root them, there's a built-in 3 that goes in there somehow.
Yeah, so him being able to use the statistical stuff before we had microscopes and everything to see what
Exactly.
what
Yeah,
they
he
were
was
doing.
like in 1880s or 70s, I think. Yeah.
Yeah, so he found out about 3 degrees of freedom and all that stuff without microscopes.
Yeah, exactly.
Electron microscopes.
Yep. Now, the reason why earlier I kept the equation the same is because I would like to freedom to be able to go back to the graph, copy this, and paste it here and say, what would the distribution of nitrogen look like if the nitrogen was at a temperature of 3000? So I can just simply change the temperature here. You see that? And you can really analyze now what happens to the distribution of gases as the gases get hotter. Let's go like this. It kind of flattens out, but you see here. So what happens when the gas gets hotter? By tenfold. More of the particles of the gas are traveling at a faster speed.
Yeah.
You see? Now what's the maximum V probable? Now we find out V probable, we go like that. Well, I think it's locking in there. Yeah. It seems like that's the V probable right there. That's the 1334 is the speed that maximizes, but only 24 particles are moving at that speed, do you see? Why? Because it's a more flatter curve.
Yeah.
Now what's the average velocity is going to be somewhere here, and then the root mean velocity is going to be somewhere here. You see? Now what if we go, see, you can continue copying and pasting and changing one thing at a time. Daniel, you could show this to them now, I mean tomorrow too. Once you have this, right, you could do all kinds of cool things with it. Just change the temperature. Let's say the temperature of the gas was 30 Kelvin. Now what happens? Well, now what is its distribution? 30 Kelvin. You see, the blue one. So you see what's happening? It's kind of like Dion's law, the one that we saw yesterday, although it's not really related to that. As the temperature of the gas gets cooler, less particles are traveling slower. You see here? I mean, more particles are traveling slower. The maximum, the V probable is 133. 248 particles are traveling at 133 meters per second. The average is probably somewhere here. See, that's what I want to do is I want it like this, but freeze it. It won't freeze. Then the V root mean square is probably somewhere here. You see? Now, what happens if you don't change the temperature, but you change the gas? You can copy it like this. Paste it. Now let's say you have carbon dioxide gas. What's going to happen? So what's the molar mass of carbon dioxide?
That's
44.
32.
40. CO2 is 44, right?
It's oxygen 16, carbon's 24.
No, carbon is 14. No, carbon is 12. 12.
12. Yeah, 12. So then 32 plus 12.
Yeah, 44. So where does that go? I think it looks like that's the only one where the molar mass goes.
Yeah.
0.44.
Yeah, that's the only one.
Isn't there another one here?
I don't think so.
Oh, yeah. Up here in the E.
Oh, yeah. Hey.
Okay, let's compare. For example, let's compare. If you don't want all this junk, just go like that. Okay, now focus in on really what's happening here. So, okay, this is the molecular distribution of, which one is which? This one is, oh, this one is the nitrogen at 30 degrees Kelvin. And this is the carbon dioxide. So what's happening here? For carbon dioxide, it's shifted to the left. You see, it's a heavier molecule.
So more of them
If
are
both of them are at the same temperature, then what's happening?
Then the
V probable is lower, the average is going to be lower, and the
root mean
square is going to be lower, right? But the number of particles traveling at that speed is going to be like 311 here, whereas this one, the number of particles are going to be 248.
Yeah.
So you see, you can change any factor. Once you got this equation, you can change any factor that you like and see how that affects it. You could also change, let's say we did, just change the number of particles. So then the only thing that would change is the 40,000. Let's say 400 particles, or let's say 4,000 particles. Okay, now let's eliminate this guy. Let's eliminate this guy. Okay, so this is both carbon dioxide, but one is a container that contains 40,000 particles, and then the other one is a container that contains 4,000 particles. What's the only difference?
There are the less number of particles.
Yeah, so does it change your V probable?
No.
Right. 106, this is 106. The only difference is that on this one, you have 311 particles going at that speed. Here you have 331, so it's 10 times less.
Yeah. So
okay,
in order to keep that same temperature with less molecules, more of them are going to be...
particles is not changing it much. So we can kind of see now the effect of changing particles, changing the molar mass, and changing the temperature.
Yeah.
Cool, huh?
Yeah.
I think that's the only things you can change: temperature and okay, guys.
Particles.
Have a good night. Relax a little bit. Do some homework, and then I'll probably see you in the site tomorrow morning.